So scenario 1, scenario 2. You got the beginning material and your ending material. Your beginning material, your ending material. The arrow means yields or something has happened. You're deciding in your head, and I'm going to call on somebody, which scenario is a physical change and which one's a chemical change. Be prepared to explain it though. You can't just say, oh, number 1 is chemical, but I don't know why. You got to give me an explanation. Just give me 30 more seconds. Good job with the homework. Everybody did it. Except for Hannah, Mackenzie, and Morgan. Almost perfect. But they're not here, Slayton, so let's show them they're not here. All right, who thinks they know? Max knows. Tell me, Max. Number 1's physical. Why? Okay. Didn't the arrangement of these change too?
Number 2 changed chemically because the atoms no longer together.
Very good, very good. He is absolutely right. This is a physical change. This is a chemical change. I was giving him a hard time. He said the arrangement of atoms changed. Well, the arrangement changed technically, but he's right. And I'll explain a little bit better. This is chemical, and what you said is exactly right. Here you have a molecule, 2 different elements. This could be like magnesium and sulfur. This could be MgS, okay? MgS, magnesium sulfide. And you have 3 of them. Well, it goes through some sort of reaction where it actually decomposes, that's what this is called, where you break it apart into smaller pieces, and now you only have Mg and S. So what you're doing is you're breaking chemical bonds and forming individual elements. If you take a compound and separate it, that's chemical. And that's very good that you notice that these were touching, so they're chemically combined. When you break that, separate it, now your individual elements, now they have completely different properties than this compound here. It went through a chemical change. We're going to talk more about that today. Up here is a physical change. So this would be, I guess we could use the same compound. I'm trying to think of something better. Maybe nitrogen oxide, NO gas. Okay? And then when you cool it down to a ridiculously cold temperature, it solidifies. So maybe we take a gas and we solidify it by cooling it down. It's still NO. You didn't change anything. Nothing changed. The composition stays the same. You just took particles that were spread out and put them close together. So that's a physical because it's the opposite of sublimation. That's called deposition. Gas to solid. So that's a phase change. That's physical. The bonds and the chemicals composition is not altered, but down here it's altered because it looks different than when it started. That's another way you can pick it out. Any particle diagram where your product and reactants don't look the same, what does that mean? The individual particles don't look the same, that's a chemical change. If they do look the same, that's a physical change. Questions? This is a big deal in chemistry, this particle diagram stuff. Any questions? Nope. I'm sure it says no. All right, let's go over the worksheet. This side first. I'm going to read it quickly here, so stay with me. If you have questions, please let me know. Blue color, physical property. Density, physical property. Flammability, chemical property. Solubility, physical property. I'm going to stop. Questions on the first 4. Please ask me if you got it wrong and you don't know why. Why is solubility physical? Maddie? Why is solubility? Do you know what that word means? How well it dissolves, right. So why is that physical? need a little bit more. So let me rephrase the question. So we know it's physical. That means the composition doesn't change. How do we know that about solubility? The molecules stay together. They stay the same. Yeah, when something dissolves, you don't actually turn it into anything new. How can we prove that? Evaporating the water. I'm going to do that today. I'm going to show you that even if you know it, we talk about it, I'm going to show you, okay, that happens. So its solubility means how well it dissolves, and that's definitely physical. Dissolving is physical. 5 and 6, both chemical, reacts to form H2O. Anytime you form something new, it's chemical. Combustion, that's burning things. Chemical, you're making new things. You have fire, light, smoke. Sour taste, like coffee. What was that? Me too. Sour taste, like Sour Patch Kids. Who likes Sour Patch Kids? My mom used to buy me, when I was a kid, like a 3-pound tub of those things from BJ's or something. I would just house those things. I would just sit down. I would go through in a week. And lucky my teeth didn't fall out. Anyways, I love Sour Patch Kids. Don't really eat them so much anymore, but sometimes treat myself. But anyways, back to sour taste. Sour taste. I'm going to say chemical. Why? I take a Sour Patch Kid, put it on my tongue. Why is that a chemical property? Pat?
Chemical composition changes.
Yeah, if you eat something or chew on something or lick something or your tongue is in contact with something, what's happening on your tongue that's changing the composition of whatever's in there? What's your body, what happens in your mouth when you start eating food or chewing it or whatever? Yeah, your saliva breaks it down. So you start breaking the food down in your mouth chemically, okay, using your saliva. You could argue with me it's physical, right? You could argue saying just because something's sour doesn't mean it's turning into something new, but if you're starting to taste it, it's going to start changing. Melting point, physical. Any phase change is physical, like this, okay? You're not altering the composition. 9 and 10, both chemical, because reacts, right? Chemically react. Form something new. Form water. Form gas. Hardness, how hard something is. I can hit this table. Ow, it hurts. It's hard. I didn't change the table, okay? That's physical. Physical. Boiling point, physical. Something boils, you're just changing phase, not the composition. 13, chemical, neutralize a base. If you ever had an upset stomach and you take Tums or Rolaids or whatever, that's what you're doing, number 13. You're popping Tums. Tums are a base. When they hit your stomach acid, they get neutralized. But really what's happening is the Tums are neutralizing your acid. But it's the same concept. That's definitely a chemical change, chemical property. Luster. So I can look at this tin. It's kind of shiny. It has luster. That luster that I'm saying that it has doesn't change this, right? It's physical. That's a physical property. Something being shiny is a physical property. Remember, things that change the composition are chemical. And odor. So, I don't know, cooking some bacon in the morning. Smell the bacon. You smelling the bacon, does that change the bacon? No, it's still bacon. Okay? So odor is a physical property. If the odor changes, right? So if something has a smell to it, and then that smell changes because it's rotting, a food, let's say, that's a chemical change. That's different if the odor changes. But just observing the odor of something doesn't change it. That's physical. All right, here we go. I'm going to call on you. Get ready. Sodium hydroxide dissolves. Monique. Physical. Dissolving is physical. Number 2, hydrochloric acid reacts. Brady, what do you think? Chemical, yes, it's forming new stuff, producing salt, water, and heat. 3, a pellet of sodium is sliced into, Kira.
Physical.
Physical, very good. 4, water is heated, changed to steam. Earl. Physical. 5, potassium chlorate decomposes. Dylan. Chemical, yes, to produce. You're producing, it doesn't say that, but it decomposes and it forms something new, potassium chloride and oxygen gas. So decompose is definitely a chemical process. That's this right here. Breaking things down, that's decomposition. Iron rust. Kaylin, what do you think?
Chemical.
Chemical, absolutely. it turns a different color, right? So we know that that's chemical. 7, sodium catches on fire. We saw this. Emily? Chemical for sure. 8 and 9, both the same answer. Cassie? Physical, phase changes, liquid to gas, evaporation, liquid to solid, ice melting, right? Solid to liquid, I said that backwards. Solid to liquid is melting. Milk sours. Max? Chemical, good. Sugar dissolves in water, Marcy? Physical, good. Wood rotting, Michaela? Try again. Chemical. Why though? That was probably one of the toughest ones on there because it's confusing. Because I'll get back to you. If you have a piece of wood sitting in the woods and it's rotting, okay, it's still going to be wood, but the parts that are breaking down are turning into new substances. In other words, eventually, if a tree falls, eventually after years and years and years and years, what happens to that tree? It rots, it breaks down, and what happens to it? It goes back into the soil. It's no longer the tree, so it's no longer wood. So eventually, it will turn into something new. That's why it's a hard question, because it's not something we observe very quickly, but eventually it would break down completely, like this, it would decompose, and turn into something different, and go back into the to the dirt, to the soil. Rotting carcasses do the same thing. That's kind of gross, but roadkill. Okay, if it just lays there long enough, it will decompose. If the birds don't eat it first or something else, it will decompose and eventually go away. Bones will be left over. So rotting is chemical. So that was a tough one. Sorry. Pancakes cooking on a griddle. Pancakes. Who likes pancakes? Everybody likes pancakes. What kind of pancakes? That's what everybody says. I personally like, banana's pretty good. Apple pancakes. Apple pancakes are the best in the world. I would like to dive into a pool of apple pancakes and eat my way out. Wouldn't be a pool really, because it wouldn't be liquid, but you get the point. What's the answer here, Laura? 13. Don't guess, think about it. Think about what you start with and then what happens when you're done cooking them. Is it the same as before? Is it the same? In other words, what do you need to make pancakes? Give me some ingredients. A box. All right, hold on. Let's help her out here. We're going to make pancakes from scratch. Flour. Probably not sugar, but you could add some. Flour, eggs, milk or water. That's kind of it, really, to make simple pancakes. So let's just say those 3 ingredients. Milk, flour, eggs. After you cook the pancake, do you have any milk, flour, or eggs left? Well, it's not. It is in it, but you can't look inside the pancake and eggs will pop out. Or milk. Right. What am I getting at? It's chemical. They went through a change. So you change the composition. There's no longer an egg, flour, and milk. They combined and they went into a different, they went through a chemical change. Their properties are different now. Would you agree? Yeah. Yes. Okay. So the properties of a pancake are very different than the properties of an egg. Okay? Cooking is definitely chemical. You're breaking bonds, forming bonds. You guys ever have a hamburger? Of course you have. Okay? Now, what color is the meat before you cook it? Red. What color should it be after you cook it, for the most part? Brownish, right? It might be a little pink or whatever. But again, color change, right? Pancakes, color change. I'm just making sure we understand that. Cooking, whether you're frying or grilling or baking, it's all chemical. Except popcorn. Popcorn is not chemical change. What happens when you take a popcorn kernel, put it in a popcorn maker or a pot or whatever?
Guess what?
It pops. Or right, microwave. I forget. I make popcorn in a pot, and my lid is see-through. So I sit there and watch it and pop, and I get excited like a little kid. Every single time it happens, I'm like, oh, it's cool. It's awesome. Pop, 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 and then it's so good, so I get hungry. So what happens? Why does it pop? It heats up. Yes. No one in here knows? Why popcorn pops?
We don't ask why, we just.
Or how? The kernel? Not that kind of kernel. Earl?
Doesn't the stuff inside expand?
What's inside?
The white stuff.
There's white stuff. There's something else actually that creates the expansion much faster with more force.
Water.
What'd you say?
Water?
Yeah. There's water inside those kernels. Think about that. The kernel's sealed, and there's a little bit of water. If you heat up water enough, what's it do? It boils. So it goes from liquid to gas. And if you trap gas in a sealed container, it builds up. If you have a gas in a sealed container and you heat it up, what does it build? Pressure. And then what's it going to do eventually? It wants to get out. That's why popcorn kernels pop. Because boiling water turns to steam and it expands. That's why it pops. So that's physical. That's actually a physical thing. Back to this. Grass growing in a lawn. That's definitely chemical, right? Hopefully you understand that. The roots absorb the nutrients, water, nitrogen, other good things. And the inside, I don't know what the term is, whatever's inside grass is changing, allowing the grass to grow. All right? So the seed, right? Let's say you start with seeds. Don't look the same as the grass. It's not like inside the seed, you have these long, thin grass pieces inside the seed, and it just opens up and it just shoots out. It actually grows and turns into grass. That's a chemical process. It's like babies turning into adults. Okay? Babies aren't mini adults. They go through chemical changes to become an adult. So it's chemical. Anytime something grows, it's chemical. Well, anything that's alive. Tire inflated with air. Physical. Food digested in stomach. It's both. Did you know that? It's mostly chemical. But did you know your stomach actually turns and churns the food? You ever get like hunger pangs? That's because your stomach's doing that and nothing's in there. So your stomach actually is physically grinding food too, not just chemically breaking it down. 17, physical for sure. The paper towel does not turn into something new because it's absorbing water. All right, take out your notes. Oh, you already have them out, right? You already went over this. Here's what we're gonna do here. First of all, you have book work due tomorrow. Kind of a lot. You'll survive. It's not hard, it's not difficult, it's more of what we just talked about, okay? So I'm gonna go through that tomorrow really quick. Chemical, physical changes, that's what the book work is on. I'll send the text out later. Don't forget your quiz tomorrow on all the elements. I haven't really reviewed it with you. You're big boys and girls, you can study that, so don't forget that tomorrow. And okay, that's it. So let's move on in our notes. So yesterday we talked about chemical, physical changes. I wanted to show you this particle diagram, so we did that. We're good. Someone quick, give me an example of a chemical change. An example of a chemical. How do you know if you're seeing a chemical change? Shout it out. Color change. What else? Fire. What else? Odor change. Smoke. What else? Light. What else? Precipitate produce, which is a solid. New product produce. Good. One more. Gas produce. Good. Physical changes. The ones I want you to remember are phase changes. Melting, freezing, boiling, condensing, subliming. That's solid to gas. And dissolving. Solubilities. Dissolving something in water. Those are really the only physical things you need to remember. All right. Good. Now, let's talk about mixtures, elements, and compounds. So I think what we'll do is we'll talk about mixtures first, then elements, and yeah, we'll talk about mixtures first. All right. So we already kind of talked about these, but I want to go into more detail with mixtures. If we don't get the elements and compounds today, we'll do that tomorrow after the quiz. So mixtures are a physical combination of at least two substances. And we know a substance is an element or a compound. So, but that's not actually true. Let me rephrase. I mean, you can write it. That's fine. Physical combination of at least two substances or mixtures. What? That's confusing. A salad. Okay? If I'm going to make a salad, I don't know, depending on the day, let's get some romaine, tomatoes, I like onions, peppers, green pepper, red pepper, whatever. Maybe cucumber if I'm feeling spunky. I don't really like cucumbers, they kind of have no taste, but whatever. So let's say I put those 5 things in the salad. None of those 5 things are compounds or elements. A tomato isn't a compound. It's not an element. There's no tomato element. Okay? So you can take mixtures and mix them to make other mixtures. I just want to make that clear. Okay, this banana is a mixture. And it's weird to say that, right? But it's not an element or a compound. Remember, there's only 3 things in the world: element, compound, mixture. So that's what I mean by or 2 or more mixtures. So you take a tomato and you put it in a bowl with some lettuce. That's a different kind of mixture. All right. So that's physically combined. So this is really important to separate. To separate mixtures, you must use physical processes. In other words, you put it together physically. Hey.
Why were you on the bus? She's clearly coming right now. Still.
So Mackenzie, real quick, after class, I'm going to talk to you about when you're free, because the lab, I'll talk to you after class. We went over the homework. You can show me that after class. We had something on the board that you're going to have to see. You can get the notes from somebody if I want to explain it. And we have book work due tomorrow, and don't forget the quiz tomorrow. Okay. All right. Separate mixtures. You must. So you put them together physically. You separate them physically. So let's talk about that. Let's talk about the different processes we can use to separate mixtures. So think about Max. Can you do me a favor? On that second lab table, there's 2 solutions. There's the blue solution and a clear one. Can you bring them both up, please? In between, or right near the hot plate. Yeah, those 2. Thanks. Yes. Hey, actually, you know what, Max? I want one more thing. I'm sorry. Can you get the ring stand with the funnel and the beaker too, please? Sorry. I was going to have everyone go back, but I just decided we'll do it right here. So we're going to talk about how to separate 2 types, right? There's 2 types of mixtures, which we'll talk about in a minute. Again, we've already talked about it, so it's not crucial to write the notes. Thanks, Max. Steady hands. Stick it right in there. All right, good work. Thank you. All right, so we have 2 types of mixtures. We have salt water, we have copper 2 chloride solution. Okay, these are, what type of mixture? Homogeneous. Homogeneous. Okay. What's this? Italian salad dressing, but what type of mixture? Heterogeneous. Heterogeneous. Why? What's the difference? Lots of different parts. What's the composition here? What's that word? It all looks the same. What is it? Uniform, right. Which one of these, which one can I filter? What if I pour this through the filter paper? Let's find out. Let's do science. You can watch that if you would like. To separate mixtures, one process is what I'm not doing right now. It's not working, but what's that called? Filtering. Filtering. Filtration only works for heterogeneous. It only works for heterogeneous. So, and I guess it took me longer to go over that stuff in the beginning of class. That's okay. Tomorrow I'll show you more of this stuff. How would I separate the copper 2 chloride from the water or the salt from the water? How would I separate these 2? And I'll show you tomorrow. Max. Evaporate. Right. Evaporation. Okay. Evaporation. Boiling. That's another, right? Boiling is kind of evaporating really fast. So these 2 are for homogeneous. And I'll show you that. How about this word right here? What's that? Distillation. That is a way to separate mixtures. Again, these are all physical process, filtering, evaporating. What's distillation? I showed you this the distiller back there. What does it do? I explained it. You take tap water and do what to it? Distill it, yep. Boil it. So you take the tap water, okay, so you have the tap water in some sort of container. You don't have to draw this right now. Add some heat to it. So this is tap water, tap H2O. And then what happens to that water when you boil it? Evaporates, right? So you're going to have vapor coming off of here. So then what happens is you have this container here. You trap the vapor. So the vapor gets trapped. And then we send it down a tube into another container. It's a really crappy drawing. But this now comes down here. And this would be pure DH2O, distilled H2O. And then you have a bunch of junk. Some of you in that, was it today's lab? I showed you the thing the other day. I took it out and showed you again. The other labs have no idea what I'm talking about. I took apart the distiller because I got to clean this part of it. This drawing looks nothing like that back there. But this part gets so dirty from all the junk in the tap water, I have to clean it with vinegar, hot vinegar. So you boil water, the water evaporates, we collect the vapor, and then the vapor is just pure water. That's called distillation. Okay, that's called distillation, and that works for, I want to define it, but that works for, I guess both, but mostly homogeneous. I get, you know, you could argue tap water is heterogeneous, but distillation, separating a mixture using different boiling points. And we'll end with this. I'm going to talk more about it. And we're going to sketch a picture of that tomorrow. But let me show you something else. No, we're not done yet. I'm sorry. I didn't mean literally we're ending right now. Give me a couple more minutes. Sorry. So let me explain this better. If we have a container and you have three substances, yes.
I don't know if your iPad is taking a photo anymore. There's a thing on this.
Something's going on? Thank you. Oh, someone's FaceTiming. We're good. It's not me. It's on a network. So like when someone else is using an iPad for something on the same network, it tells me I'm doing the same thing. I don't know. So back to this. Thanks, Emily. Let's say this has three liquids in it. Let's say we have ammonia, NH3, we have water, and we have, why can't I think now off the top of my head? Let's go with, ethanol, CH3, CH2OH. So we have all three liquids in this container, and we want to separate all three liquids from each other. One way you can do it is heat it up. Water boils at 100 degrees. Water boils at 100. Ethanol boils at 80. Ammonia boils, I forget, I want to say like 90. Okay, 90 degrees. All three boil at different temperatures. So if we had some sort of valve up here, where as we heat this one's going to boil first and evaporate, we could collect it. Then this one's going to boil next, we could evaporate and collect it. Then water would boil last, we could either leave it in there or collect it. So that's another way to separate mixtures physically, is by using boiling points, and that's called distillation. Okay, that's called distillation. So this is really mostly for homogeneous. Okay, because filtering doesn't work. Look what happens. You can't filter that. It's the exact same thing. Okay, filtering doesn't work. Can I filter this? Want to see it? Let's do it over here. You guys ever see one of these things? It's like a T-ball strainer thing. That won't open. Haha, here we go. Observe the glory. It's filtering. What's getting stuck on top? If you want to see it after class, you can come up here. It's disgusting. But this this will filter. How come I can't use that filter paper? Yeah, it's too fine. What happens is the oil gets all gunked up and it won't actually filter. So I'm just being dramatic. You can filter heterogeneous, but you cannot filter homogeneous because it's all dissolved. It goes right through the filter paper. All right. So we'll stop there because I'm almost out of time. And tomorrow we'll pick up this conversation. Don't forget the book work, quiz tomorrow, and I am after school.